Welcome to Lesson 14C, Filters Part 2, Diffusion Effects. We're going to continue to discuss air filters. We're going to introduce a new model called the Cheng model to account for diffusion effects. By way of introduction, the Calvert and Englund model, which we've talked about, is single fiber collection efficiency, and it counts only inertial separation and particles that impact the fibers. It does not model the diffusion effects due to Brownian diffusion, which are important for very, very small particles. There's many models for diffusion out there. I'm going to discuss only one. This is the only one that we'll use in this class, and that's the one due to Cheng. Here's a reference. I'm going to give you a lot of equations here. Here's the procedure for the Cheng diffusion model. First, we have to calculate the diffusion coefficient between air and a small particle. This is very similar to the DAJ that we used previously, except that was for gases, some kind of air pollution gas and air. A means air and J was the species. Well, here it's AP because P is the particle, A is still the air. So here's the equation for that. And we're using the Boltzmann constant, which we've seen before. For all these quantities, I'm going to give you the units. This one would be in meters squared per second, just like any other diffusion coefficient, as we've talked about. Then we need the filter solidity, which we approximate as just 1 minus the porosity. By the way, there's a C in this equation. That C is the Cunningham correction factor of the particle. Alpha is non-dimensional. Now we calculate something called a Kuwabara hydrodynamic factor. This is just another correction factor, dimensionless, and it's in terms of this alpha. Then there's something called a Peclet number, which is another non-dimensional parameter like a Stokes number or a Reynolds number. It's defined as the fiber diameter times the speed coming into the filter, and then this diffusion coefficient that we just evaluated. That one also is non-dimensional. And then finally, this is the equation for the Cheng model. It needs the Peclet number that we just calculated. It needs this Kuwabara factor and alpha. As you can see, this is an empirical equation, and it's a single fiber collection efficiency. It is a grade efficiency since it's a function of dP. DAP, for example, will change when dP changes, and therefore Peclet number will change, and A to F will change also. And this Cheng model accounts for Brownian diffusion. Well, we've already had the Calvert and Englund model, which accounted for inertial separation and impaction into the fiber. So just like we did with raindrops, we just add the Calvert and Englund and the Cheng models into a total single drop collection efficiency. From there on, all the equations are the same as what we had previously with Calvert and Englund. Let's do an example. Here's an air filter that's cleaning dusty air. Now, I'm using all the experimental data of Heinz, which was a plot that I showed in the previous lesson. I'm trying to duplicate that plot. So let's see how close we can get. In Heinz filter, the filter fibers were 2 microns in size. U0 was 10 centimeters per second or 0.1 meters per second. Porosity of the filter was 95%. The total thickness of the filter, which we call L here, is 1 millimeter. Particles of interest were 0.2 microns. I couldn't find in any of the references what the particle density was, so I'm leaving that a blank, but what I did was use 6500, which after trial and error gave me the best fit to the plot that he had. He also never said the temperature or pressure, so I assumed it was SATP. We want to calculate the collection grade efficiency of this filter for these particles as a percentage. So I duplicated all the equations, and I'm going to do it all by hand, but of course you want to do this in software to avoid making any kind of calculator errors. But I'll do it here to make sure all the units work out, and just as an example. So again, I'm going to use 6500 as the particle density, which ended up being the best fit. Particle density minus air density times particle diameter in meters squared, U0, and then epsilon. 18 mu, then 2 microns is the filter fiber diameter. These are the numbers that Heinz used. And don't confuse the filter fiber diameter with the particle diameter. One is 2 microns and the other is 0.2 microns. I'll give all my numbers here to 4 digits. It comes out to 0.04111. Non-dimensional. Let's make sure. Kilograms, meters, and seconds all cancel. The Calvert and Englund single fiber collection efficiency is thus 0.007778, or about 0.78%, which is pretty small as we expect for inertial impaction with such tiny particles. That's all review from last time. Now we get into the new model, the Cheng model. This one accounts for diffusion. So first my diffusion coefficient, Boltzmann constant, temperature, Cunningham, where I'm not showing the calculation of that, but the Cunningham correction factor comes from the same equations which we used before. And these are for the particles, 3 pi, mu, and dP in the denominator. And now some unit conversions. A Newton meter is a joule. A Newton is a kilogram meter per second squared. Joules, newtons cancel, kilograms cancel, Ks cancel, and the remaining units are meters squared per second, which is what we want. I get 2.238 times 10 to the minus 10th meters squared per second. Alpha is just 1 minus epsilon, or 0.05. And then the Kuwabara hydrodynamic factor, Kk, I get 0.7972, non-dimensional. And the Peclet number, make sure you use the right diameter here. This is the single fiber diameter, 2.0 microns, and then U naught over DAP, which we calculated up here, and I get 893.6. And then finally my Cheng single fiber collection efficiency, plug in alpha and Kk, plug in Peclet number, I get 0.03337, or about 3.3%. So just a comment, in this particular case, the inertial effects were about 0.78%. The diffusion effects are about 3.3%. So diffusion is dominating for these very small particles that are only 0.2 microns. Now that we have both the CE and the Cheng single fiber collection efficiencies, we have to add them together to get the total. 0.04115, and this is a great efficiency at this particular particle diameter, which is 2.0 microns. Our LC now is the same as we had last time, except we're using this total A to F instead of simply the A to F from Calvert and Englund. Pi over 4 epsilon over 1 minus epsilon df, and then this A to F at our particular particle diameter. I get 0.0007253 meters, which is very small. In fact, this filter, as you recall, was very thin. It's only 1 millimeter in thickness or length. So finally we plug that in, 1 minus exp negative L, which is 0.001 meters, and then our LC we just calculated. And I'm going to put my times 100% here to get my final answer. I get 74.8% at this particular particle diameter of 2 microns. So as I always say, put all this in software, make sure you can get my answer for this example problem, and then you should be good for the quiz. And you know by now my pattern has been for the quiz, you have one set of variables and one particular particle diameter. In the homework, you'll have to plot for a range of particle diameters. I did the same thing, and I repeated this for a range of particle diameters. And as I mentioned before, I played with some different densities, and 6500 gave me pretty good agreement. So here's my final plot. Experimental data of Heinz are here, and my calculations are in blue. This is actually very good agreement. There's a lot of approximations in all of these calculations. Sanity check, here's 0.2, which is our particle diameter of interest. I actually picked the one that was very close to that dip there, and we get just under 75%, which agrees with what we had here. A couple comments. As you can see, this Cheng model predicts nearly 100% collection efficiency for very, very small particles down around 0.01, 0.02 microns here. But in reality, that doesn't really happen. In real life filters, the actual efficiency never really reaches 100%, and it kind of falls off for very small particles. So it'll do something more like that. There are some models that correct for this 100%, and you'll see a curve like this if you apply some of those models. But we don't have time to cover those models in this course. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.